Hello students, let us continue our discussion on urban ecosystem. Today's topic is demonstration of urban ecosystem and water. So let us try to remember what we have discussed in the earlier classes. Last class we discussed water cycle, pools and fluxes, the flows and processes. Key processes in the natural water cycle we discussed. Then we discussed the modified water cycle. We have discussed the key urban water challenges, and then we came to the solution side. Integrated urban water management and its many different aspects we discussed. And lastly, we concluded that discussion with the policies and the paradigm shift for future. So, one particular lesson we took from the last class is urban water security. You remember those 6 cities, mega cities, their problems we discussed? And we could actually experience that urban water insecurity in those cases. There are more cases like that. So, let us first discuss once again the urban water security, followed by certain good examples how to really take care of this problem. Urban water scarcity, population growth, urbanization, and climate change, they are stressing conventional freshwater resources which are available in rivers, lakes, aquifers. Many arid and coastal regions are having lot of cities now, and they are already having the over exploited water regime. This necessitates a turn towards the non-conventional water resources, many of which require significant technology and energy to become usable. But in urban environment, that is quite acceptable. Lot of good technologies are coming and energy is also available. So what we see that in the urban water security issue, the paradigm shifts are happening. Integration, adaptation, innovation, cooperation, we are discussing about them. In last class only, we discussed that integrated urban water management. With that, we can also see the key policies are also being in place to take care of the future water security. Decentralization, resource recovery, like waste is a resource. That is a very important policy. Smart water grids, climate resilience. Climate resilience through diversifying the water portfolios are wonderful policies now in place. So let us look at some good examples. Today we will be discussing demonstration cases on this desalinated water, atmospheric water, dew and fog, recycled water, water pool conservation, we will be discussing snow, and we can easily understand that all these can help us in future urban water security. So let us go for these cases one by one. Desalination. It's a process that removes dissolved salts from a saline water source like seawater, brackish water. Don't you think this is actually happening naturally, desalination? Yes, it is happening. But that is not sufficient in urban areas, because in urban areas the demand is much larger which nature can serve. So we have technology. What are the technologies we are using? We are learning from nature only, obviously, and now we have developed technologies to do those processes faster and more efficiently to handle large amount of waters. First one is the reverse osmosis, a membrane-based process. High pressure is created to force water molecules to pass through a semi-permeable membrane. and leaving the salts behind. So, this is the basic principle for reverse osmosis. It's a very dominant modern technology and its success depends on the energy efficiency. The other technology which are very prevalent in the desalination is the multi-stage flash distillation. The previous one was a membrane based process and this one is the thermal based process. What you do? You heat seawater under high pressure and then you start passing it through lower pressure chambers successively, series of lower pressure chambers. And thus flash is happening to it. What is flash? Sudden vaporization. How it is happening? You have a high pressure chamber, the seawater is heated there, you are bringing to a low pressure one, its boiling point will go down now for the water in that lower pressure. So, it will have a boiling point low and it is having heat. So, it will be additional heat will help it to vaporize. So, that's the way the flashing will happen. So, the steam will be the result of this low pressure chamber movement and which is then condensed and collected as distilled water. So, this is again an energy intensive one. Let us see which are the countries who are using it. There are n number of countries now who are using the desalination as major process. I am bringing the example of Israel and we will also discuss Israel's integrated water portfolio. I think all of us now we are quite aware about Israel for the Gaza-Israel, Palestine-Israel war. But believe me, Israel has many other things for which we can always look at them closely to learn. They are very strong in technology. Israel is located in an arid region, so it is always having limitation in the natural water source. Low rainfall is there and very high demand from a growing population and productive agricultural sector. Even if it is a desert, they have very strong agricultural activities. So, a severe water crisis in 2000 catalyzed adoption of an integrated water resource management program for Israel. And it was then formalized in the National Master Plan for 2050. There are three pillars in this particular integrated water resource management approach. First one is the large scale desalination. It's not lab scale. Laboratory, we are doing the desalination. No, it's a large scale industrial desalination. World leading wastewater reclamation and very importantly, aggressive water conservation. For that, people's participation is important. Israel has a global dominance in seawater desalination. It has 5 mega scale seawater reverse osmosis plants and they are among the most efficient ones in the world. These plants are supplying over 80% of the domestic urban water for Israel's cities. The Sorek complex is the apex of this technology. Sorek 1 produces 6,24,000 cubic meter per day and the next one is planned to produce 6,72,000 cubic meter per day and at a record low price. So, that is the fit of the technology. Next we will be discussing that is the wastewater reclamation for Israel. Just see this particular image, seawater they are taking that is coming to the desalination plants. From that human beings in the city, in the agricultural field, they are using it. After usage, the wastewater is coming out, that is getting collected and sent to plants. Here the example has been given for the Shavdan plant, how it works. What it does, it treats this wastewater and brings out the solid waste, that is the fertilizers, and that is being used in the agriculture. The liquid, the reclaimed water, that also comes to the agricultural field, and the gas, the biogas, that comes as a electricity and heat, and actually making sure the plant is working, getting that energy flow. And from the agriculture field, we can see again the human beings, they are getting the supply. So you can see it's a very strong mimic of the closed loop of nature. The water is being collected and continuously being utilized and recycled. Israel enjoys global leadership in wastewater reclamation as well. It reuses nearly 90% of its wastewater, a rate 4 times higher than any other country. Over 85% of treated effluent is used for agriculture, providing more than half of all water for irrigation. This Shebdan plant, which I was showing you, the flowchart, is a UN model facility, and this treats wastewater for the Tel Aviv area and irrigates 60% of the Negev desert's agriculture. Let us have a quick look of the plant itself as the Shebdan plant. So, after discussing the desalination and the wastewater reclamation, let us now discuss the atmospheric water harvesting. And under this particular section, we will be having discussion for the dew capture and the fog capture. Both are passive methods. They will collect water vapor by condensation. Let's see how it happens. Dew, you know, it gets condensed on the surface, whereas fog, it is in the atmosphere. Dew capture, that collects water vapor by condensation on surfaces. What are the principles utilized? On clear nights, a surface with high thermal emissivity radiates heat and gets very cool, and this cooling, when reaches below the air's dew point temperature, then water vapor gets condensed on these cool surfaces. So that's the principle used. Technology, let us see the technology side. Uses the optimized condensing surfaces, often spatial foils, or surfaces inspired by nature, biomimicry, like Namib Desert's Bittleback. You can look at this particular example. It's a wonderful example. You read about it. The viability, you have conditions when it can work best. That is clear night sky, high humidity and low wind. These are the necessary conditions for having the dew capture appropriately. Next one is the fog collection. Fog collection means we are harvesting liquid water from fog events in the air. And you can see on the right hand side of the slide, there is a nice image of the fog collection system. So, large vertical mesh nets are erected perpendicular to the wind. From the sea, the wind is coming towards the land, and it's a perpendicular route where our meshes are. As fog passes through, droplets collide with the mesh, coalesce, and run down into a collection trough. So, in the lower part of this image, you can see the collection trough. The technology used is normally polypropylene mesh. Advanced designs are also there, like fog hub is being used, where parallel wears for higher efficiency are being deployed. The viability, when it is optimally done, That is, it is best in coastal or mountainous area with frequent advective fog and consistent wind. Advective means horizontal. It's not moving vertically up. It's horizontally moving from one place to the another place. Strategic contest for this fog harvesting, that means we are trying to get water from the air. It is viable water source, especially in arid coastal or mountainous regions where wind pushes dense fog through these collectors. And these concepts are actually being applied already. In the Morocco, Darcy Hamd project is one such project. It serves remote Amazigh communities in the anti-Atlas Mountains who faces severe water stresses. And this particular project alleviates the daily burden on women and girls who traditionally fetches water. So it's so very socially meaningful initiative as well. So science can be like that. Chile also has a good example in the Atacama Desert. Projects like Falda Verde provide water for communities, one of the driest places on earth, enabling economic activities like agriculture. Technological architecture for this fog harvesting is equally interesting, very fascinating. Large vertical mesh nets are erected perpendicular to the wind, a passive low cost system that requires no energy input, which already we have discussed. Fog droplets collide with the mesh, coalesce and drip into collection trough. But in addition to this one also there are two more interesting alternative techniques. So you can see the first technique, that mesh, is here. The second one is a device that includes chemical absorption and desorption processes. This is that example. And the third one is promoting the condensation on cold surfaces during the night. This C is actually showing us how to do this. So this fog harvesting is being experimented in many different societies now because it has shown its efficiency. Performance of this fog harvesting, it depends on the site. Yield is highly site specific. The Morocco project which I was discussing, Anti-Atlas, that reports yields of up to 22 liter per square meter of area per day on foggy days. The technology is economically competitive against alternatives like water trucking in remote areas. That's the only alternative. We bring water from other places. In comparison to that, in that particular locale, you can do the same thing. Now let us explore its potential in the Himalayas, Sikkim. While no large-scale fog harvesting projects are documented in Sikkim or other Himalayan states in the region, the fog harvesting concept poses the necessary climatic condition for the technology to be viable. The eastern Himalayas, including Sikkim and Darjeeling, are described as fog-rich environments, making them ideal for this technology. Fog harvesting is particularly suited for mountainous regions or else desert region and could supplement water supplies where conventional sources are stressed. What other relative water initiatives we can find in this region? The success of fog collection in nearby Nepal demonstrates its applicability in Himalayan context. So that's a very good proof that yes, it can be applied in similar geoclimatic areas. Sikkim is already implementing innovative water management strategies like Dhara Vikas initiative. It is doing a wonderful job rejuvenating springs through rainwater harvesting. And Jalkund, micro rainwater harvesting, showing a readiness for alternative water solutions. So, States like Sikkim can easily start experimenting with this fog harvesting. Next section we will come to, that's the recycled water. In this, we will definitely would like to discuss Singapore's NEWater. As a water-stressed island nation with no natural aquifers, Singapore faced a critical national security vulnerability, historically relying on imported water from Malaysia. So you just imagine a city come nation is completely depending on the neighboring countries for the potable water, very basic need. So definitely Singapore has worked on it and they have brought the four national tap strategy for a diversified resilient water supply. What is the first tap? Water from local catchment. So rainwater harvesting to the fullest extent possible. Imported water, that is also obviously a continued method. NEWater, that's the recycled water and the desalinated water. So these are the four taps for the country. NEWater and desalination are the two weather resilient taps, providing a drought proof supply. NEWater, highly treated reclaimed wastewater, and that is currently meeting up to the 40% of Singapore's water demand and is projected to meet 55% by 2060. So just see the capacity of this reclaimed wastewater. Technological architecture, let us have a look at it. It's a three-stage multi-barrier purification process. First one is the microfiltration or ultrafiltration, which removes the suspended solids, bacteria and some viruses. Then in the next stage, it goes for the reverse osmosis, which removes over 99% of dissolved impurities, including salts, ions and organic molecules. And the third and final stage, ultraviolet disinfection, a final safety barrier to inactive any remaining microorganisms. So now it is safe for use, even the potable use. So performance and governance in a country like Singapore, you have to always bat for the quality. So the final water quality is superior to the WHO and US EPA drinking water standards. Just imagine, where most of the countries are having problem to reach that standard, their reclaimed wastewater is getting treated and it's superior to the standard. And 300 plus parameters are getting monitored in these different treatment plants. The Changi plant operates at a low cost of Singaporean dollar 0.08 to 0.15 per cubic meter. So low. Governance and public trust. Success was built on a multi-decade public engagement campaign by the PUB to overcome the yuck factor. Whenever we think about, oh, it's a recycled, you don't easily accept that. Psychological factors are there. But there lies the success. How they have done it? They have gone for branding. Transparency at the NEWater Visitor Center. You can come and you can look at the process. You can look and taste the water. Community participation. So these are several important things which helped the NEWater of Singapore to be a global example. Now we will come for the last segment of today's discussion, that is water pool conservation. Spring shed, watershed, pond, lake, they are all good examples of water pool, fresh water. Streams. Today we will be discussing one which is snow or ice. So water pool conservation, the example I have chosen, that is from Ladakh, the Ice Stupas. water towers, a wonderful water storage and management strategy from the hills of Ladakh. The stupa are constructed by temporarily freezing and holding water in a solid state to be used later in the years when it is required. Channeled water from higher altitudes is sprayed into sub-zero air. It freezes, this is sub-zero air, it freezes immediately into towering ice formation capable of holding millions of liters of water. This technique is an adaptive measure used in cold, arid regions like Ladakh to address water scarcity caused by the climate change. And these water towers are having interesting history also, which is innovation history, you can say, is built upon the traditional glacier grafting. The concept is built upon the traditional glacier grafting and the work of engineer Chuang Naufel that has inspired the people who have worked later. He created horizontal artificial glaciers in 80s. In 2013, engineer Sonam Wangchuk, the vertical ice stupa, which is more resilient at higher altitudes as its conical shapes minimizes the sun exposure and the snow melting. Technological architecture, let us have a look at it. This image also shows the same thing, that the water is coming under the gravity. Under gravity only it is going up and then it is getting sprayed and it is coming down as snow because the sub-zero temperature is there. And during the summer season, when they will melt gradually, they will be taken to different areas where it is required. The system is very simple and gravity powered, requiring no electricity for its basic function, but it's a conceptual one. Later on, we have seen lot of good technology have been deployed into this particular simple concept. Water from a glacial stream is channeled from a higher altitude through an underground pipe. Gravity pressure forces that water, which I was showing here. Pressure forces this water up a vertical pipe where it is sprayed out of a nozzle into the sub-zero winter air. The water freezes immediately as it falls, gradually accumulating in layers to form a massive cone of ice, like an ice cream. Performance and scale. A prototype was built in 2013, stored 150,000 liters of water and lasted until mid-May, proving the concept. Generally, March is the month when the stupas are being built. Dozens of ice stupas have now been built across Ladakh. The largest, the Shara Fuktse, stands 33.5 meter high and can store up to 7.5 million liters of water. So just imagine, during the April-May months, when water is required and you can get it so easily from the same snow. Now the automation has been added to this ice stupa. Manual stupas are very labor intensive and risk is always there for the freezing pipes. So smart stupas or automated ice reservoirs are using now sensors, control boards and mechanized valves to manage the water flow based on real-time weather data. Automation prevents pipe freezing, reduces manual labor and optimizes ice formation, making the system more efficient and scalable. And that is important. And what socio-economic impact it has been able to bring? Let us see that part. It is providing a reliable water source for the crucial spring sowing season, supporting local agriculture and food security. It is reducing water disputes among the villagers because now the resources are available and it is also influencing the decreasing trend of migration to towns for employment. The project is a model which fosters the community engagement, often through Ice Stupa competitions. Every year they are having this competition, and thus the way it connects with local culture, because they name these structures, these stupas, after the Buddhist stupas. So, a good example, I hope you enjoyed. So, today we have discussed desalinated water, atmospheric water, dew and fog harvesting, recycled water, NEWater we discussed, water pool conservation, snow. These are the references. Please go through them. Thank you.